Okay, I think we'll get started now. So thank you everybody for joining us on this one-on-one track at the GSC. This is session 3Q, where we welcome Dan Rule, who'll be sharing with us some exciting history about the mainframe and also what we have to look forward to in the future as well. If you do have any questions, then Dan is quite happy to take them throughout the session. So I will allow you all to unmute yourselves in a few minutes. But if you also want to enter your questions or comments in the chat, then please feel free to do that also. And before I hand over to Dan, I just want to remind you to please complete the feedback form at the end of the session. And I will put a link in the chat afterwards to make it easy for you to access that feedback form. So with that, Dan, I'll hand over to you.
Thanks, Atul. This is called Mainframe at 60. You can hear me okay?
Yes, we can.
All right. Hardware and software foundations for the future. It's somewhat of a misnomer, the title, but I'll be talking about some of the history of the mainframe. But a lot of the focus is basically a mainframe 101 course, just to talk about the basic components of the mainframe. It's foundationally been around for a long time. And as this slide shows, I've been around for a long time too, 48 years in capacity, performance, cost, and operational management. I was first a tape operator in the early machines that we'll see a picture of one of those. I do some presentations across different conferences and attend different conferences. I'm involved with Sharon in the US. And also I am a bicycle rider, and it's two of my bikes actually there, my road bike and my hill bike. So that's me. This is what we're going to go through. We're going to talk about core. Core includes hardware and software enablement. We're going to do, there's in the back, I should mention, there's technical terms, which I'm not going to go through, but there's so many acronyms in our world. So I put a glossary of technical terms in the back, and there's additional detailed slides because there's so much to talk about this platform. All right. This is a slide that just says, what are the differences between a mainframe and distributed server? I was a manager of capacity in a couple different companies, both mainframe and distributed for capacity management. So I had both spaces. The last job before the current one, I had also a network. But the mainframe is really a relatively small box, and then the boxes for storage are similar size. So these boxes scale tremendously. So you can imagine the differences between the environmentals of this footprint and these fluoroform footprints across all the racks that you might have servers in. So this side, the cost per unit is cheaper. Scalability is larger on the mainframe side. You could put tens of thousands of servers in this box. Back in 2002, there was one company that put 40,000 servers on the box, and that was back in the early 2000s. So that the scalability of this machine is unbelievable. And also AI is slowly creeping into this environment with workload manager. Workload manager, we'll talk a little bit about that later in the slides, is basically gives priority to the work and runs the machine, if you want to, at close to 100%. That's how workload manager works. It's able to do that, giving different priorities to the work. I'm not going to talk about every slide in detail, so hopefully you'll be able to download it later. I have notes in the slides. This gives you a scalability from an industry perspective. Is the mainframe still alive? Yes. The answer is a firm yes. Most of the banks run mainframe. Most of the ATM transactions go through mainframe. Passenger flights, I worked at Delta. We had a couple mainframes at Delta. Credit card transactions, I worked at JPMC. They have credit card transactions there. So it's all the large institutions are running mainframe. 1964, these are the machines. I used that little blue button there, the IPL button, initial program load. I started back in 1976 on a box like this. This was my box was a 360 60, and it looked like this. And these are the tape drives here. We're gonna have, there's another picture. This is the punch. This is where punch cards get read in and also created through there. These are the tapes when I was a tape librarian. I would log into tapes manually on a piece of paper, and then it would go over into key punch. This is 64, and this is today's mainframe. So there's been a lot of changes. There's not any real tape anymore. It's all electronic. These tapes, you know, the next generation of these tapes went into cartridge tapes, like a VHS cassette, smaller than that. But these were the tapes that I initially did back in 76. This is the machines they used in the Apollo Moon program. April 7th, we're on the 60th anniversary, hence my title. I took advantage of the title to talk about Mainframe 101 stuff. So physical tape, these are the printers. I was, you know, I loaded the paper into the printers. There was printer tape that was part of this that you would create to be able to programmatically run printouts into there. This is the processor. You know, this is the processor now. You know, channels are here, and these are the channels. So you can see that these are disk drives back here. There was no cache. It was physical I/O. So when you put a data set or a file next to another file on the physical platter, it would potentially impact performance. So if it was a real busy data set, sometimes you would move the data sets around because it wasn't, there was no cache or memory in that environment. This is the card reader where we would read into jobs that would run on the systems. And today, this is the Z16. 40 terabytes, 190 cores or engines, 32 terabytes of memory. And then this is, it's a huge, huge amount of memory that's available, you know. So there's memory here now, and there's memory on the box. And so both of these together provide extremely good performance. You could get lost in the detail on this, but the main thing that I would like you to get out of it is that over time, every couple of years, there was always a new generation that came up with a new generation of the machine. So this is continually being improved over time. 7 nanometer CPU cores. There's 200 of them. There's 40 terabytes of memory on this Z16. And you can see that the capacity over time has also increased. This is at some level, you know, you have spec ratings, you know, over in the distributed world. But this is a way to relative nest intensity, LSPR. Whenever you do a benchmark on any kind of computer, different benchmarks, depends on the type of work, will have yield different capacities in the box. And so there's a something called LSPR that IBM publishes: low, average, and high. Relative nest intensity, when it's high, means it's heavy use of memory in the hierarchy, which is really good. Low means that you might need more capacity to run that work. In other words, it didn't get any memory hits. So that's what this is about, is that there's an LSPR rating that gives you, and there's links here, you could go read about it some more if you want. But this is what this is about. The LSPR rating is the spec ratings of this environment. There's also a term of MIPS. MIPS and service units are also mapped into this LSPR rating. And the size of the KEC is Central Electronic Complex. I got to remember to talk about the acronyms, what they mean, which is the machine. The LSPR rating matches to the amount of work you could push through, which is expressed in MIPS, millions of instructions per second. It's not MIP, it's MIPS, plural form. It's millions of instructions per second. And then there's also service units. And usually that's expressed in MSUs, or millions of service units. Those are normalization numbers, and LSPR references those. There's different types of engines. All the hardware is the same, but the microcode that runs on it is different. So there's the central processor where CPU and I/O goes. All workloads, including Unix system services, is run over there. This is where all your pricing, IBM pricing and other vendors might price you on this, on the CPs. If it runs in zip, there is no charge if it runs over on zip, and there's a certain amount of workloads that are enabled to run in zip. You know, every workload usually has to do CPU and I/O, so it's only the CPU portion of the transaction would run over there, which is DDF, which is remote DB2, or Java will run on zip. And there's other assembler codes that might be enabled on zip too. IFLs, these are engines in order to run ZVM and Linux. ZVM is a virtualization technology. We'll talk about that later. And then finally, ICF, Integrated Coupling Facility, that does CPU and I/O. The coupling facility engine allows data sharing, which enables sysplex. So you could have record row locking across different systems or LPARs. LPAR is a container, and a system which the operating system runs is where the system runs. You could be updating the same table but a different record if you enable data sharing with the ICF or integrated coupling facility. Why is more memory better? So, you know, the previous slide, I said there's tons of memory on the Z16. These are the high-level reasons why more memory is always better. Substantial latency reduction, or in other words, response in online workloads, increased transaction rates. In-memory databases see significant gains in response time by avoiding I/O wait. You know, that's part of the transaction response. And then batch load reduction, more concurrent workloads, shorter elapsed times. You know, the work gets out of the system faster if you could put it in memory and not have to do I/O throughout the I/O subsystem. Sysplex. So I talked about the Sysplex. You know, there's multiple engines on a CAC. You know, this could be one machine. The ICF or the coupling facilities can be in the CAC, or it can be external coupling facility. I don't really talk about it that too much in this presentation, but each image talks through the coupling facility, which enables to be able to share data and do record level locking if you want. There's also some system services that come across, like messaging, that go across through the ICF or the coupling facility. There's two kinds of utilization. There's a logical process utilization. We're going to see an LPAR mapping of what this is really about from a physical perspective. But there's measurements with state of busy of the logical CPs. It's independent measure of capacity. And then it's a physical process utilization. This is the physical process utilization. It's the actual physical machine and what that is doing from a CAC perspective. This is what's used in capacity planning in order to measure, you know, and trend what is necessary for number of MIPS or service units that you might need, or CPU seconds. I put this together. This is kind of really a summary of all the things that have been going on by decade, from a hardware software API enablement. Back in the 70s, I started in the business. And then in the 80s, we got a 370, 158, which was one MIPS machine. And in the 90s, we moved on to CMOS, and things changed as a result of that. And then finally, we're in 2024. We have Z16. We have a processor now that can do AI on the chip. That's what this is about. Tell them. And then software from MBS. I was running MBT back in the 70s, and then we're SOS 3.1 or Z 3.1. And with WLM, that came in 3.1. WLM is now AI enabled. Workload manager. And then there's all this enablement. I'm focusing here on all the IBM products, but there's certainly also other OEM products that are part of this Z infrastructure too. For instance, there's other security products. Go ahead.
Yeah, can I just ask you mentioned the WLM is now AI enabled. Can you just explain for us what does that mean in real terms? What benefits?
Yes, I could. I have a slide. Can we hold that question until last?
Sure.
I have a slide that talks specifically about that.
Of course.
Workload manager, just as a prep for that, workload manager, what it does within a sysplex. Let me go back here. Within a sysplex, the work comes in on one of the images, and then the workload manager at the sysplex level has a policy, and it looks at all the utilizations across the sysplex. Pre-AI, it would, if the utilization was low, it would just send it to that low usage. But if the job, like 15 minutes into it, suddenly starts using a lot of CPU, it wouldn't really know anything about it. So it's gotten smarter with AI. So it really does a lot more work in terms of trying to balance the systems better across the environment. And I have a slide that just talks about that. So that's a kind of a partial answer. Hopefully that helps.
Yeah, thank you very much. That's good.
All right. So we talked about LPAR management, what runs on Z-Frame. So within Prism, which is PR, this guy right here, virtualize IO, it virtualizes all the IO across all the engines that are across here. Now there's a CP engines, there's zip engines, there's IFLs. The IFLs are for all the Linux boxes. Here we have Linux on Z running on Prism, on bare metal. Here's Linux running on ZVM. ZVM runs on Prism. So there's a lot of options. There's KVM that can run on Prism and run Linux. And then you could have ZVM running Z over here, a test and development system. So there's a lot of options with this Prism environment. So, there's virtualization that are possible over on the distributed side. This has been around since the 70s, Prism. So this is really where all the Z work runs. It runs across Prism as a hardware enabler across all and it assigns engines to all these environments to be able to run. This is a map, and there's another map in the back of the deck that gives a little more detail. There's different areas within the address spaces within Z, and this is a high-level look at why do I care? So the more memory you have, that's why you want to go to 64-bit on Windows, and same thing over on the mainframe side. You have more data you could address in memory. So that's what this is about, is when you're 64-bit Z, you have a lot more memory that's available, up to 16 exabytes of memory. Application workloads run in the private areas, and then all these other areas that are part of which is in the back of the deck, but there's other areas that system tasks run within the environment. You'll hear this term, the bar, a 2 GB bar. That's what this is right here, 31-bit, 2 GB, and then extended memory at 64-bit. This is very difficult to understand. All right, what kind of work? What's the work that runs over the environment? There's batch jobs that run. Users could submit batch jobs, and also scheduling systems submit batch jobs. They can run batch work. Users, when I say users, that includes scheduling systems. Batch jobs use job control language, or JCL. So does started tasks use JCL, and actually TSO users actually use JCL too. Probably should update my slide here to say that. TSO users are the interactive users where you log onto the system, going and logging on, and you can edit data sets, you can submit batch jobs, you can monitor the system, you can look at the log, or it's called the syslog on Z. And then started tasks, they can be started with a start command into the syslog, into the console, and that can be run. Those are the type of works: job, TSU, and STC. And then there's numbers that attach to, a job number. So it'll be a job number or TSU number, a start task number. You'll see that in the messaging when you look at the syslog, what kind of workload it is. It'll say the number and whether it's job, TSU, or STC. One of the pieces of work that run in the environment is the transaction server for ZOS. It's CICS or KICS, is a family of mixed language application servers. And so many varieties of client access can be run across this. You can do REST services, JSON, SOAP, MQ, SNA. And different business logic is available in there: COBOL, assembler, C, and Java. In environments I worked, some of our CICS transactions were credit card transactions. So it's very high response, very good response times within this within the transaction server for Zed. DB2. DB2 is a relational database developed in 1983. Has availability. So, I talked about earlier sysplex. So you can imagine if you have two DB2 subsystems and each run in a different system with record level sharing, you can keep each of those up when you bring, you still have data availability if you bring one of them down, because the other one would take over. So this continuous availability is a result of the data sharing that's enabled through the coupling facility. MQ is guaranteed messaging. So messaging uses an asynchronous model, generates message that did not have to execute at the same time, and application can consume those messages. So it talks to CICS and DB2 and other platforms, and it's multi-platform too. It's not just on Zed. It's available in other areas too. RACF runs on, this is the security product that runs over on Zed. It controls access to systems. It does many different kinds of security accesses, from data sets to accessing applications on the network and so forth. And then there's other products that are available from Broadcom, 2 products from Broadcom, Top Secret and ACF2. I'm not sure if there's any other products as far as I'm aware of, but those are other products that are available over on Zed. These are some of the products, the languages that can run on Zed: Cobalt, C++, C#, Java, PL1, Rex, so forth. All these applications are available on Zed. What programming language runs faster? Java is the fastest on Z-Frame. So if you want to run Java and you want it to run it fast, it's best on Z. And then Cobalt runs fast. Assembly language is closer to the machine code, is the fastest code that you can run. Cobalt was embedded in 1959, and then Grace Murray was the scientist that invented it. And some of Grace quotes: "It's often easier to ask forgiveness than to ask for permission." I've used that many times. Disaster recovery. So it's not just a data center that has where the work is run. One data center is where the work is run. You could have in-region and outer-region data centers. So this is kind of the architecture where you would be able to replicate data and have another process over here and be able to metro mirror or global mirror the data center. And these are the architectural technologies: PPRC, XRC. Those are all acronyms in themselves, but there's unlimited data distance support. I have some companies that I've worked at where they were 3 or 4 states away where the other data center was. Application recovery. So the Z platform creates a record of all the work it does. It's called SMF, another acronym. but it cuts these data SMF records whenever a data set's created. So having a product, which is IBM Z batch resiliency, to be able to automatically restore and know when the last update to a data set is important. So that's available for application recovery. So this is global mirrors. This is at the physical hardware level and data, and this is at the application level, this type of recovery. Capacity management. So this is kind of my last 20 years, 30 years that this is what I've been doing, is I've been a capacity planner, and that's where all my work has been. But it's capacity, performance, and cost. So capacity, scalability, performance is service levels, and cost is constrained by each of these two other rings. So this is what I've done in the past. Is that it's the same as what is on a distributed platform. Is that you have to deal with capacity, performance, and cost. You don't have unlimited money to put as much hardware on the floor as you want, and you might be restricted by the scalability of the product and also what the actual hardware can actually perform. In terms of forecasting data, the data that gets created out of Z is the SMF data again, and it creates a history which includes the workload data, the machine level data, the system data. Utilizations of the system are all part of the SMF data. And to be able to have that, to be able to have measurements and do manual analysis or AI against it is fundamental in order to manage in this environment. And this diagram here is fundamental to any platform, really. If you're running distributed, you need data in order to manage the environment from a capacity, performance, and cost perspective. And we're going to talk a little bit about Workload Manager. Workload provides the ability to run multiple workloads at the same time. It's dynamic workload management. It looks at the work as it's coming in, and it prioritizes the work based on a policy that's created by the system programmer or the performance engineer. And WLM measures and creates records on CPU, I/O, and wait. So you can tell whether or not work is where the delays are, whether or not it's all in CPU or I/O or in other wait. That's part of the metrics that come out of Workload Manager. There's two types of goals: response time, average, and percentile. It's average time to complete work, or percentage. This product is really the game changer for this platform. The Workload Manager provides the ability to run a lot of work through these machines because of Workload Manager, being able to specify the response time and match it to the business goals that you have. So if you had credit card authorizations and you had to have a 2-second response time, you could define it in Workload Manager to have the system work towards that goal. And it will try to work towards that goal and report if it can't work towards that goal. In other words, you might need to put more, either tune or put more processor on the floor to make it happen. And a velocity is to measure how fast work should be running. I was a performance engineer, capacity planner. Like I said, I would get calls, my job's running too slow. So if everybody had high priority, this is what it would look like. No one would have high priority. So this is just raise my job priority slide. So Workload Manager works best when you have different levels of priority. So raising priorities of jobs when system is 100% would actually cause worse batch throughput. All right, high priority work gets done when the system is 100% busy. So this is when you have a physical capacity line here, and you can see right here, you can see my mouse moving, right? I hope. This work here, this orange importance 2 online, the high water mark is right there, So you need enough capacity to be able to at least be able to do the high importance work. This other batch work can be delayed and it can be pushed out. So the work gets pushed out. The system right here is probably running at 100%, but response times for this interactive work is doing just fine. So this is the job of a capacity planner, is to make sure that you have enough physical capacity to run the interactive work. The batch work is important, and it has to run and finish in a certain point in time, but it's not as important as interactive work. So the constructs within Workload Manager enables to be able to do that. All right, this is my AI slide. So as I talked before, is that WM looks at SMF records, ingests the historical data, and then in real time, it predicts the upcoming workload. So it automatically starts and stops initiators and assigns resources proactively. So I know a little bit about this, probably as much as what the slide says, but this is a huge step forward in Workload Manager. Previously, I had products that would look at the work and understand the priority that's within the scheduling system and then prioritize the work, because it knows this job is going to run along, and then it would change the priority dynamically. AI, I'm expecting this to actually help in that, is when it sends work to different systems that are part of the Sysplex, it will update the priority of the work and be better at starting and stopping initiators and limiting work going to different systems. Does that make sense? Any questions?
Yeah, it does make sense. Is this implemented at many sites currently, or is it still quite new?
I'm part of Share, and when I asked who's at ZOS, ZOS, Z 3.1, there was very few people in the room. And so most people are at 2.5. There's some that are still at 2.4. And until you get to 3.1, you're not going to see this. So I think it's a small population out there in terms of experience.
Okay, it's going in the right direction, which is good news.
Yeah, I think this is great. I mean, I asked the Watson guy like 10 years ago, hey, what do you think about, doing something, making Workload Manager smarter? We got it. We got it now in 3.1. I see some chat questions here. Let's see. Oh, okay.
It's just comments for now, yeah.
All right. So highlights. So 99.999% availability. It runs legacy and modern languages. It could run on a mainframe. IBM runs Unix. I don't know if that's new news to people. As a mature hardware virtualization layer, we saw that slide where a different work can run across in one box that looks like this. AI is built into the hardware. That's at the chip level now. Enables sub-second fraud checking. That's quite a story in itself. Capacity scales to the largest companies in the world. We saw, the first couple of slides where we talked about the amount of billions of transactions that run through, a typical mainframe in large companies. Multi-system record level data integrity, data sharing using the coupling facility. So this box, maybe it has, let's say it has 20 systems on it. It could be sharing data across those 20 systems with different DB2s and do record sharing because of the coupling facility. That's what that's about. Small footprint, a picture's worth 1,000 words. Resiliency that includes out of the area redundancy, so you could there's hardware that's available that will connect this box to another box in another state or another country, I should say. Resiliency that includes point-in-time recovery, journaling. There's logs, like DB2 has a log that does rollback, recovery. If you have batch resiliency enabled, you can do batch resiliency. There's backup software that's available, which this presentation really doesn't talk about storage too much, but HSM, which is a hierarchy storage manager that does backups and recovery and archive. That's part of that. That's built into the operating system, been around for decades. Hardware components are redundant. I don't really get into this, but there's redundant power supplies and a number of redundant cores, I think, that are within the box. And then we're done. Session feedback. Any questions? I'm surprised it covered so much in so little time.
That was a lot, but very interesting.
Yeah,
And
I
quite a
just-
broad set of information. So yeah, thank you so much for that.
Yeah, and then here's the technical terms. You can look at that. There's a lot of technical terms there.
Excellent, thank you. So to our audience, really, if you do have any questions, please feel free to unmute and ask. Dan has got such a high level of expertise and experience. It's worth picking his brains, man.
Yeah, I've had a number of jobs. I've done tape librarian. That was, that was my entry level job, but I was a ZOS engineer, installed products. But I did enjoy being a capacity planner because it allows to do, look at data, do graphics and forecasting, statistics. So there's a lot of niche type jobs that are within the environment, from being a product installer to a CSS systems engineer to a DB2 database engineer, so forth.
I think you covered all the basics that people coming into the mainframe, into the new world, really would need to know and would appreciate, really. So thank you for that. We have something in the chat from PH. For completeness, I appreciate this is a high-level presentation with bias towards ZOS. When talking about operating system support, you shouldn't forget ZVSE and ZTPF. Some of the very high transactions mentioned are delivered by ZTPF, which is mainly used for reservation and credit card.
Yep. Yeah, I was when I was on the 360 machine, we had ACP4, and then we went to ACP9, which ultimately became TPF, and then finally ZTPF. And that's very high transaction. That's all written in assembler, I believe. And then my company, 21CS, owns ZVSE, which I probably should have some slides in here about that.
Okay, okay.
Yeah.
Are they, ZVSE and the TPF, are they widely used, or are they specialist, used in special industries only?
Well, the airline control industry, sorry, not the airline control, the airline industry uses ACP4, ACP9, and also TPF. Okay. I was working at Household Finance, and we connected TPF to IMS, which I don't talk about IMS here, but our ACP4, ACP9 was connected to IMS that had United States commercial lending rules in it. And so we used TPF because it was a very high response time. I've never been on VSC though, but I think I might ask for somebody for that.
Okay, okay. So maybe something to add for a future session, really.
Yeah.
Okay. So do we have any other questions or comments from anybody in the audience? Satish. Any advice to university students who have just embarked on the journey of learning about mainframe technology? Is there any particular methodology we need to apply?
A computer is a computer. That's the word. Number one, I did distributed and mainframe, and the different platforms have different response time issues. It's about the service response times. And so understanding the architecture so you know where you can tune it. I'm a capacity planner, so that's kind of where I'm coming from. On a Windows stack, it's at the high IO is a big thing at the stack level, whereas in the mainframe, it's usually memory or region size. It becomes more of a problem. I guess I would. It's experience makes all the difference in the world. So my degree is in psychology. Okay. So I have 48 years in what I do for a living here. My degree is in psychology. I learned everything in the job, and just being inquisitive is the methodology. I would always be inquisitive and wanting to learn more, and go to conferences like GSC or any other opportunities you could do and sit in and ask questions. Always sit in the front so you could ask all your questions. That's what I did.
That's a good response, actually. So from my point of view, I don't know if you guys are familiar with the T-shaped individual. So T-shaped being the top part of it is learn broadly about many different aspects of the mainframe.
Yeah.
but you might want to go down and specialize in a certain area. So you might be a software developer, but it's still good to understand, for example, what role does memory play? What role does the way a database or the kick region is defined play in the way your application runs? So
Right.
I do agree with you. Go to the multiple sessions, ask lots of questions, and grow your broader understanding also as part of that. So,
Yeah,
so
and then talk to people in socially too. I mean, when you're at these conferences, talk with them socially, ask them, what kind of machine do you have and what kind of work do you run? What kind of problems do you have? Those are good questions, whether or not it's distributed or mainframe. It's all architecture, right? And they have similar issues.
very true. And we have a good community. Everybody's willing to help and mentor each other. So yeah, don't be shy to ask for help or assistance, really. That's good. Okay. Any further questions? No, if not, then once again, thank you so much for taking time to join us today, and thank you, Dan, for sharing such insightful information. And there is a link in the chat to the feedback form, so we do appreciate your feedback, and we'll try to make future sessions even better than the great session we had today as well.
Yeah, I appreciate everybody's time, and have a good rest of the conference. I think there's a ending session later today to give feedback.
There is as well. Yes, that's right. That's right. So please do join us for the future sessions as well. All right. Thank you, everybody.